All right, guys. So we're going to continue our notes on temperature. Miss Bab just got through talking to you about temperature, and she got to this point in our notes. Um, let's look over here next. Let's look at these different examples of things. This one right here says the center of the sun, if you couldn't figure that one out on your own, is 15 million degrees Celsius. Well, that's pretty high. The highest climate temperature on record occurred in a desert in 1922. It was in Libya. And it was 58 degrees Fahrenheit, 58 degrees Celsius, my bad, or 136 degrees Fahrenheit in the shade. That is pretty hot. All right. The next one, the lowest climate temperature on record occurred in Vostok Station in Antarctica. And it was negative 89 degrees, or negative 192 degrees Fahrenheit. In space, intergalactic space is somewhere around negative 270 degrees Celsius. That's pretty cold. And then absolute is the word here, absolute zero. Absolute zero is the temperature at which something is so cold that all the particles stop moving. And it's theoretically stop moving because we really can't reach absolute zero. There's a great Bill Nye episode where he goes crazy about, can we reach absolute zero? And he's like, absolutely not, because there's always a path for heat to get in. So it's just a theoretical. We've gotten really, really, really close. And but absolute zero is going to be 0 degrees. Sorry, 0, no degrees on the Kelvin scale. So let's talk about these scales. Kelvin scale. And there we go. I'm a little laggy there on my document camera. So the first question we have here is, what are the temperature scales? Let's talk about these just a little bit more. There are 3 different temperature scales. You've got the Fahrenheit scale, you've got the Celsius scale, and the Kelvin scale. Now, on the Fahrenheit scale, it's the one we use the most, and it's the one that people know the most. We've got water will freeze at 32 degrees Fahrenheit, and water will boil at 212. Body temperature is 98.6, your internal body temperature. And common room temperature is around 68 degrees. Now, how does that apply to the Celsius and Kelvin scales? The Fahrenheit scale was created a really long time by a guy named Fahrenheit, and it wasn't, he was a scientist, but he didn't go as scientific as the people who invented the Celsius scale. The Celsius scale, I think, makes a little bit more sense once you get used to it. Got water freezing at 0 degrees and water boiling at 100 degrees. We don't have to worry about all these weird numbers like 212 and 32. Why those 2 numbers? Well, it's a long story, and I don't have time to go into it right now. But there's a reason why they think that Mr. Fahrenheit did that, but it's too much trouble to go into right now. But you can look it up, Google it. Go ahead. The Kelvin scale came along, and it is basically the same thing as the Celsius scale. See, there's 100 steps, 100 degrees from 0 at freezing and to 100 at boiling. The Kelvin scale also has a very similar type of scale, and it starts out at absolute zero, which is 0. it's the lowest temperature. Instead of 0 being the temperature water freezes, absolute 0 is the temperature for the Kelvin scale. So you actually have to go up 273 degrees to get to 0 Celsius or 32 degrees Fahrenheit. 273 Kelvin is at the temperature at what water freezes. And then a little bit more than that, 20 degrees more than that, or sorry, notice there's not a degree symbol here. There's a degree symbol here, but there's no degree symbol here. There's no degree symbols here. And it's so confusing. I oftentimes forget to say that, but it's just 293 Kelvin, not 293 degrees Kelvin. I don't really know why, but that's the deal. That's just what they say. So if 273 is the same thing as 0 degrees Celsius, 20 degrees more is going to be like 20 degrees Celsius. So 273 to 293. Body temperature is 310, and water boils at 373. So there's still 100 steps from freezing water to boiling water. All right. And then the last little section right here, what is heat and thermal energy? This is one that kind of blows people away sometimes because sometimes it doesn't seem to make as much sense. But let's first define heat. Heat is the flow of energy from warm places to cooler places. Now, heat always travels from where it's warmer to cooler. It never goes the other way. A lot of times people will say, close that door in the wintertime. They'll say, close that door, you're letting the cold in. Well, you're not letting the cold in, you're actually letting the heat out. I know it seems kind of picky, but there is a reason why they really, want you to know that. And it makes a little bit of sense as time goes on. So this is the next one. The heat from your hand travels, what do you think the word is there? Into the ice cube. And the ice cube, what do you think it does? It melts. Yes, indeed. That's really surprising. So thermal energy or heat energy is the overall energy of a system that is responsible for the temperature. And remember, temperature is the speed of the particles. It's how fast the particles are moving. Right? So increasing or decreasing this can change the state of matter of a substance. And they can't quite see that, but that says of a substance. Okay, so here's the idea. Heat energy is different from temperature. A cup of coffee can have a really high temperature. It can be 150 degrees. A swimming pool can be at a low temperature in the wintertime. You might have a swimming pool that's like 40 degrees if the weather's really cold outside. The crazy thing is there's more heat energy of a cup of coffee at 140 degrees. Sorry, there's more temperature in a cup of coffee. The temperature's higher, but there's more heat energy in the swimming pool because there's just a lot more of it. And the way you can think about it is it takes heat energy to melt ice. What if I had a really big block of ice and I poured that hot cup of coffee over it slowly? How much of that big block of ice would end up melting? Not much. But what if I were to take that big block of ice and put it in that big swimming pool at 40 degrees and swirl it around some? Do you think that block of ice would eventually all melt? Yeah, because 40 degrees is higher than the temperature at which my ice will melt. It's higher than 32 degrees Fahrenheit. So you will get the ice to melt. The temperature of the pool will drop by maybe like a degree. Maybe turn out the whole pool is like 39 degrees. The ice cube will warm up, and the pool will cool down just a little bit. But since there's so much of that material there at 40 degrees, there's enough of it to melt that cube of ice. So a cup of coffee at 140 degrees has a higher temperature, but a lower amount of heat energy than a swimming pool, a huge swimming pool full of water at 40 degrees. It's got a lot of particles in a swimming pool, not as high of a temperature, but more heat energy. All right, I think that about covers it. Miss Bowen's going to take it from there, and she's going to go over the rest of this. She's going to explain to you some things about the next section, which I thought I had a copy of that right here, but looks like I don't. So she'll go over that with you in a bit. Go to the next section.